Okay, algebra students, here we go. In lesson 2, we're going to be applying properties of rational exponents. And the first thing we're going to do is we are going to simplify some radical expressions. Now, we've done this with square roots in the past, so maybe I would have had an expression like, I don't know, the square root of 24, and I'd be asked to simplify that. Well, if you remember back when we did that, we weren't allowed to have any perfect square factors other than 1 in the radicand. So we might use a factor tree and think about splitting this up into the square root of 4 times the square root of 6. And we did that because 4 is a perfect square factor of 24. And we take the perfect square because the square root of a perfect square is a nice rational number. In this case, the square root of 4 is 2. So I got 2 times the square root of 6, and that was a simplified version of the square root of 24. We can do the same thing with cube roots, fourth roots, fifth roots even, if we follow kind of those same ideas. So no perfect nth powers in the radicand. So if it's a cube root, no perfect cubes. If it's a fourth root, no perfect fourth powers in this radicand. And no radicals in the denominator. We'll run into those in a little bit. So a couple of ways that you can go about doing this. And I'll show multiple ways, so you pick whichever one works the best for you. If I want to simplify the cube root of 81, one method that I could use is I could use that factor tree idea. If that worked for you before, it probably will still work for you now. I'm going to split this up into 2 factors of 81. The key is I want to look for a perfect cube that is a factor of 81. Those might not be numbers I know off the top of my head, but over here I've given you a table of those values. So I've got x values, and then I've got what x squared would be. So here's a list of perfect squares. And then here are the first 6 perfect cubes to go right after that. And then first 6 perfect fourth powers, etc. You could have a list like this handy if you wanted. This would be one way to do it. So what I would do is I would think to myself, well, what cube goes into 81? Well, I would take the biggest one possible. Well, 64 is big, but 64 definitely doesn't go into 81. So I just kind of work my way down the list. Does 27 go into 81? Now, if I'm not so sure, I can always check on my calculator. Let's take 81 divided by 27 and see what we get. We get 3, a nice rational number. So that means 27 is a factor of 81. With that info in mind, what we would do then is split this up into the cube root of 27 times the cube root of the leftover factor, which in this case would be 3. Now, I picked the cube root of 27 because that's a nice number. The cube root of 27 is 3, because that's what I cubed to get 27. So this expression turns into a 3. 3 times the cube root of 3 is what this would look like when I'm all done. 3 doesn't have any perfect cubes as factors. So there would be my simplified radical expression. Another way to do this that might be easier for some of you is I might take this 81 and use a factor tree just to find all of its factors. So 81 I know is 9 times 9, and 9 is 3 times 3, and this 9 is also 3 times 3. And then what I could do is I could rewrite this expression as the cube root of those 4 3's multiplied together. 3 times 3 times 3 times 3, etc. Now, if I'm looking for a perfect cube factor, well, a perfect cube would be the product of 3 identical factors. Well, guess what? I've got 1, 2, 3 identical factors right here. Because I have 3 3's multiplied together, the cube root of these 3 3's multiplied together will be 3. So because there's 3 of them inside the radicand, and I'm looking for perfect cubes, I could take a 3 out. I write it outside the radicand. Then I multiply that times the cube root of whatever the leftover is. Well, in this case, there happens to be an extra 3 left over, so I'll write that on the inside. So 3 times the cube root of 3, same thing we got with the first method. Let's do that with the fourth root of 240. Using method 1, I would look for a perfect fourth power. So from this list, what of these goes into 240? Well, 256 is off my list. Maybe 81 if I get really lucky. I could always try it. Doesn't hurt. Take 240 divided by 81. And no, I get a decimal. It's no good. So my next option then would be to take 240 divided by 16. So we'll try that. 240 divided by 16. And we get 15. Oh, look at that. So 16 goes into 15 times. So I have the fourth root of 16 times the fourth root of 15. And again, I do that because the fourth root of 16 is 2. So I'm going to have 2 for that part of the expression, times the fourth root of 15. 15 does not have any perfect fourth powers that go into it. So that would be our simplified version of that radical. Again, if I were to do it the other way and write out all the factors, it would look something like this. I have the fourth root of 240. So I'll just copy down here. I would just make a factor tree with 240. Think about, let's see, some easy factors here. We'll go with 24 and 10. And then the factors of 10 would be 2 and 5. Factors of 24, we're looking at 4 and 6. 4 factors are 2 and 2. 6's factors are 2 and 3. So then if I were to write the whole thing out, I have the fourth root of, I'll make that a 4. 2 times 2 times 2 times 2. I could have written 2 to the fourth, but just for the sake of the example, we'll write it this way. So there's all my prime factors of 240. I'm looking for fourth powers. 1, 2, 3, 4 2's means I can take out a 2. 2 comes out, multiplied by the fourth root of whatever's left inside. Well, 3 times 5 is left inside, and that's 15. The same expression that we had up here.